this quarter, the math class focused on a totally different topic from what we did last quarter, which was statistics. And moving on this quarter, it was all about the different functions with inequalities and linear programming, along with using the technology of graphing online. And thus, we also wrote equations in different types of structures. So, in the big project, we did contribute greatly into science, which I will talk about in the end of the video. So, here it is, my big project for this quarter. So these are the ideas on why we're doing the big project and what indicates us to do it. So this is the front cover of my big project, which consists of the table of contents which leads you the steps of how I do the project. So this is the page where the introduction is placed, and it is where I define the problems along with my research questions and the hypothesis. So before going into further details, this experiment is what a piston of an engine. It rotates. A compressed air and a fuel mixture produces greater forces in an uncompressed mixture, where the gases ignite and a spark plug. So we want to know the relationship between volume and pressure for a 60 cubic centimeter syringe attached to a pressure sensor. In a dedication to Boyle's law. As you can see, many things are involved of me doing the big project. Firstly, and most important of all, is research. To carry on with observing the relationship between volume and pressure on the syringe, Boyle's law is the main concept, and we don't know what Boyle's law is, so that's why we need to find out more about it. The next two methods I use are scatter plots and exponential functions, which I will talk about in the standards in the near end of this video. Most importantly, technology is what contributes to this project very well. I used the software GeoGebra to create a scatter plot where the data is given, helping analyzing the relationship of the data in a very sufficient and more accurate way than doing everything by hand. As it in the results, the volume continues to decrease, the pressure increases continuously, based on how the x-axis of the graph increase while the y-axis of the points decrease steadily. Boyle's law also states that the equation of an ideal gas is PV equals nRT, where P is the pressure and V is the volume. The rest is in science. So pulling back the plunger increases the volume syringe, which decreases the pressure. As it said, it's inversely proportional to one another. Thus, from research, Boyle's law stated that if the temperature remains constant, the volume of a given mass of a gas is inversely proportional to the absolute pressure. Furthermore, from the graph, it clearly shows us the results of Boyle's law. Since the higher the volume is, the lower the pressure is. Thus, in terms of algebra, the graph which expresses the relationship between two variables is written as y equals 25.1438x to the power of 0.974, which is the form of an exponential or a power function, is one of the standards we did cover, and I will talk about it more in near end of the video. In terms of the discussion and conclusion, the outcomes of this research based on the scatterplot with an algebraic expression as said before is that the hypothesis I made before was accepted since the outcomes of both the research and the graph contributed by the help of GeoGebra based on the given data that shows that the two variables of pressure and volume are inversely proportional. Based on the results, it can be implied that Boyle's law was proven correctly as well, since in terms of science he said temperature is what makes the two variables inversely related to another. To force gas to increase both the volume and pressure, massively increase its temperature, then you'll see. This course is designed to give us students real-world situations and problems that often involve many things around us, in which our system of learning are the Common Core standards. This quarter, we focus on inequalities and linear programming. And furthermore, at every end of each standard, we must answer three essential questions, which are, what did you learn, how did you know you learned it, and why did you learn it? Starting off with the first standard, which is ASSE 2. And what's it all about is to use the structure of an expression to identify ways to rewrite it. And in this case, I did a lot of factoring and recognizing the GCF in terms of worksheets and doing it in my notebook. And the reason we're probably learning this is because it's very useful, since the skills of rearranging and evaluating expressions will be called upon in almost every math class you take. In which I know I have learned it since I did a lot of practice questions and I was sufficient by doing it. The first step to writing a new equation is finding its greatest common factor, which is the greatest common factor, and you simplify the equation at its simplest form based on dividing the GCF. And in a more complex step, it is grouping, which is shown on the screen on how I do it in terms of GCF as well. And in the test, I did get a 4 out of 4, so it's this proving that I do understand this standard quite well. The next standard I covered, which is FIF4, it says for a function that models a relationship between two quantities, interpret key features of graphs and tables in terms of the quantities and sketch graphs showing the key features given in a verbal description of the relationship. Again, I did do a lot of practice worksheets based on the equations, which allows me to be sufficient. And the reason we're learning this is that functions are very important since we are critically using them for economic planning and development. And in terms of this unit, we learn to find the x-intercepts and y-intercept along with the vertex and evaluate whether the function is increasing or decreasing. Moving on, FIF5 is similar in terms of context. Building up from FIF4, it is relating the domain of a function to its graph. Again, I did a lot of problems based on this topic, and the reason though we've learning this is because everything has limits. Even though your graph, in real life, there are limits. And I know I'm very learning this well because I know how to graph the domain and range in Desmos. Thus, applying the graph to the problem solved. In FIF6, which is another build-up from FIF5, is to calculate and interpret the average rate of change in a function. Which in this case, it's like finding the slope of the graph to see how much the variables change in each step, whether it's x or y. I did again a lot of practice questions on my notebook, which they are in relating to standards FIF4 and 5. And as for the tests, they are all combined on a Monday in October. So because they're all about functions, which I got a 4 in FIF4 and 2 3s in FIF5 and FIF6, which is probably because I missed a week of school. I didn't catch up, but now I get the idea of the functions pretty well. In FIF7, it is still about functions, but in this case, in 7b, we graph square root functions, which in terms we graph by hand, and in each equation of the square root determines the different slope, which determines the different shape of a graph. Absolute functions. We all know then the graph is never negative and the equation is based on y equals the vertex times the absolute value of x minus m plus n. Learning this though about radical and absolute values can allow you to predict the future, thus making measurements about the snooker table, and many architects can use it too. The next part of FIF7, which is FIF7c, is all about polynomial functions, in which they could both be either linear or quadratic. Going through this standard, I've come up that even degrees polynomials are either up on both ends, while all the odd degrees polynomials behave on their ends like cubics. In this case, we could see the graph in Desmos and the algebraic expression based on the degree of the polynomial on GeoGebra. In which this case, we could use polynomial functions to solve in terms of physics, business, and many things. Thus, in FIF7e, it's all about graphing exponential and logarithmic functions, showing intercepts and end behavior, and trigonometric functions showing period, midline, and amplitude. In terms of logarithmic functions, they are inversely proportional to the exponential functions. In terms of real-life problems, we find the domain and range, which are the limits of the problem, thus the exponential growth based on the rate of change and the amount of time used. In terms of trigonometry, a periodic function is the one which repeats itself all over in a horizontal direction. We project the values of sine theta from the unit circle to the set of axes on the right. We obtain the graph y equals sine x, and we expect the period to be 2 pi. And as in y equals a sine x, it affects the amplitude, and the amplitude is absolute value of a. Moving on to a brand new standard, yay, which is CED2, is to create equations in two or more variables that represent relationship between quantities. As on how they are similar to each other, ACED is also combined at the same standard since it represents the constraints by equations or inequalities and by systems of equations or inequalities and interprets solutions in viable or non-viable options in a modeling. The steps of this standard are based on linear programming, which is first defining the variables, then write the objective function whether it's maximum or minimum, write the constraints in the form of inequalities, and defining the feasible region, find the feasible solution, and then find the optimal solution. And another tool that could help you in this standard greatly is Desmos. Moving on to another new standard, which is Array 2, is to solve simple rational and radical equations on one variable, which in terms of a graphical language, it is where the graph intersects. I have learned that as different formats of equations occur, there are different ways to find its solutions. And in terms of that, we could determine whether it is possible for something to happen in real life. If it doesn't happen, it means there's no solution. The last standard of this quarter, which is using technology to find the coordinates, is essential since we want accurate results in real life. Since we want accurate numbers to determine that nothing goes wrong. The rest of the standards we're due to take them next week. In the big project, not did we just cover the standards in math, we did also the standards in chemistry in relating to the gas law, PV equals nRT. And as for the activities for the rest of the quarter, we also did some practice tests on the SAT, in which for some of us, it is the goal of life.